Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Genevieve Schroeder with us today. Hello, Genevieve.
Hi, thank you so much for having me. I'm so excited.
Well, thank you so much for talking about your very awesome article, which we will get to shortly. And Genevieve, what's your geolocation? Where are you at?
I'm in Ithaca, New York right now. It's April 8th and snowing, so we love that.
Hey, so we get some April snow angels or snowballs or things along those lines.
Yeah, that's what brings May flowers, right?
Yeah, so they say. So it is April 8th, and I'm in Phoenix, and we will probably hit our first triple digit Fahrenheit probably in the next couple of days. So I think we're kind of sort of in the opposite spectrum here between Ithaca and Phoenix. So mm,
Yeah, maybe we can level out and it'll be more average temp for both of us.
yeah, we
That
should
would,
somewhere in the middle. I don't know, Iowa or so
yeah.
we'll get in the middle. But yeah, very cool. And Genevieve, what is your position there in Ithaca?
Yeah, so I'm a postdoc at Cornell University with I'm working with Dr. Anna Ho.
Very cool. Very nice.
Yeah.
And as long as we go down that route, Genevieve, what do you like to do research on?
Yeah, so I like to study relativistic explosions, specifically with radio telescopes.
Ah,
So my PhD research at Northwestern University focused on gamma ray bursts, but at Cornell, I've sort of broadened the scope to a bunch of different relativistic transients and seeing what's up in the radio.
very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The long-lived broadband afterglow of short gamma ray bursts 23111-7A and the growing radio detected short gamma ray burst population. And Genevieve, take us away.
Yeah, thank you. So first, I do want to thank all of my amazing co-authors. You may see that there's a ton there. Getting observations of these gamma ray bursts takes a lot of effort from a lot of people, and it's not possible to do it alone. So I appreciate each and every one of them, and especially, of course, my PhD advisor, Wenfei Fong.
Mhm. Very cool. That's a great shout out. Very good. Okay, let's go ahead and get into it.
Yeah, so just to sort of give an idea of the main event that is in this article, it's GRB 231117A. That's typically how we say it. Um, and it was a short gamma ray burst that went off in November of 2023.
Yes.
So a short gamma ray burst is a uh, explosion that occurs typically when two neutron stars merge. You may have heard about it when, LIGO detected its first binary neutron star merger. That was accompanied by a short GRB as well. So
Mhm.
people care a lot about these events, and especially because they create heavy elements such as like gold and platinum and fun, shiny things, and some of the elements that we need to like exist as humans.
Yes, very cool. Good,
So
good.
we've been studying them for a really long time, trying to sort of understand what's happening during these explosions and what there is going on around them as well, and how often do they occur.
Cool. Very good.
Yeah, so the radio side of these events, they're called gamma ray bursts, but why are you looking at them in the radio? Well, first of all, they're these relativistic jets that are being shot out very quickly, and they're interacting with a lot of stuff that's around this neutron star merger. And that interaction is accelerating electrons and producing synchrotron radiation. And synchrotron radiation actually can be observed from the X-rays all the way down to uh, the radio frequencies. So that's why we look at them with radio, even though it's the complete opposite end of the
Reverse.
electromagnetic spectrum.
Very good. Okay.
And the radio is really important because it actually tells us a lot about the environments that these events occur in. It's how bright our radio afterglow is, which is this emission that I'm talking about, is super dependent on how much stuff is like in the near vicinity of this merger. And also it can catch some really interesting extra components that aren't this like standard forward shock that I just explained, which we'll get into later.
Okay. Okay.
Um, and then the very human side of this event in particular is that this event occurred when I was in the middle of applying for postdoc jobs. So including the one that I have currently,
Ah,
it was kind of crazy to try and like observe this while also, being in a application cycle.
mm-hmm.
Um, and
Mm-hmm.
then also the fun thing is for whatever reason, these events never occur on a Tuesday. It's always Thursday, Friday, Saturday, like
Of
when
course.
and always when your life is the busiest. I don't know why that is. We should do a statistical study on this at some point, but
Make sure we
uh,
put some Bayesian machine learning on that just to, make it seem real.
yeah,
Very
yeah.
cool. Very cool.
Um, so
Yep.
this event, yeah, it's really great because we have a beautiful data set for it. It was first detected by the Swift telescope, but also a bunch of other gamma ray telescopes. And the Swift telescope is amazing. I was just at the 20th birthday celebration in Florence, Italy for it,
Mm-hmm.
but it's really great because it slews automatically to look at these events in the X-ray, so we can get really early time X-ray observations. Whereas with optical and radio, there are some ways to slew things automatically, but a lot of these are like human-led processes.
Yeah.
So it takes us a little bit of a buffer time in order to get our observations.
Very cool. Okay.
So yeah, you can see we can scroll through this observation section, and it's quite long because we acquired so much data. So yeah, there's gamma ray
Gamma
observations,
rays,
there's
X-rays.
X-rays from Swift, there's X-rays from Chandra. Uh, we have a ton of optical data from so many different places.
Okay. Yay.
The super exciting part about the optical is that we were able to get the redshift of this event, and it's at 0.257.
Ah.
So
Okay.
that's relatively low. I think that's a little bit lower in the paper as well. Um,
It's actually in here as well.
yeah, it's in the,
Pinpointed. There we go.
yeah,
Yeah,
exactly.
it's probably a little farther down too, but okay, yeah, relatively close at 0.257.
Yeah, in terms of short GRBs, that's pretty close. And we'll see that later when we start talking about the overall population.
Okay.
Um, And we had some really cool optical afterglow data. It was really well sampled. And of course, we looked at it in the radio. So the radio was first observed by ATCA, which is an Australian compact array telescope.
Okay.
And what was exciting is that it was pretty bright in terms of like a radio afterglow. So we uh, had already initiated some very large array observations by the time that this ATCA detection had come out, but it was exciting to see that for both of these telescopes, we had bright detections, which typically means that we are able to track these these events for a very long time.
Nice. Very nice. Okay. With
So
you.
if you look, yeah, at figure one, this is our observations from Keck, which is in Hawaii.
Mm-hmm.
And we can see the optical or the host galaxy as well as the optical afterglow
Mm,
underlying.
nice.
So the left panels are G and I band. G's on top, I's on bottom.
Yep.
And it looks very bright. That is the afterglow. You can see in the middle panels, there's this faint host galaxy. So not nearly as bright as its optical afterglow.
Mm-hmm. Mm-hmm.
And then the right panel is the subtraction of the two,
Okay.
just to get the best idea of how bright the optical is without the host galaxy getting in the way.
Right. I'm with you. We got some circles here. What do these various circles mean?
Yeah, so they're the localizations for the different telescopes and where we think the afterglows are. You'll see that the XRT, which is from Swift, doesn't line up with everything else.
Yeah.
It's a little funky. This isn't the first time I've had this issue. We're not too worried. The Chandra, since we did observe with Chandra,
Hmm.
the X-ray afterglow from Chandra lined up really well with the XRT
Yes.
afterglow. So it's not like we were observing two separate things. It's just sometimes astrometry is hard.
That it is. And we shall forgive XRT here for a moment.
Yeah, it's
It's on
old.
it's on target. It's on target.
Exactly. It got the data that we needed, and that was what mattered.
Cool. Very good.
So if you scroll to figure 3, figure 2 is just some spectrum stuff from the optical side. I appreciate all of the optical astronomers in my paper, but it was not the part that I found to be the most interesting of the paper. But again, they work very hard, and I'm so grateful for all of them.
And I am too. On to,
Uh,
on to figure three. Radio.
Yeah, so this is the radio afterglow of not only the GRB in question, which is these green stars, but the entire radio detected population, as well as a bunch of non-detections, which you can see as these like
Um,
filled in triangles. Those are the least interesting
right.
part. Uh,
Okay. Mm-hmm. Mm-hmm.
and so you can see how, the green stars, this is in flux density space, so just how bright it appears, not how intrinsically bright it is.
Yes.
But you can see the green stars are some of the brightest. So again, this means we had really high signal to noise detections, which is awesome. It means that we could also observe it with with a couple different like frequency bands to get a lot of interesting radio coverage.
Right.
And also, thanks to how bright it was and where it was on the sky, it actually was a great target for both Meerkat, which is a radio telescope in South Africa,
Huh?
and ALMA, which is a millimeter telescope in Chile.
Yes.
So you were able to observe not only with the VLA, which is typically my bread and butter, but with these two other really awesome radio/millimeter telescopes. And this was the first event to be detected with all three. Our radio detection coverage was almost 2 decades of frequency, which is
Very nice.
beautiful.
Beautiful. Plus, it's bright enough here you can actually watch it evolve over time scales of 50 days or so.
Yeah, which is awesome. You can see from some of these events, like these weird yellow colored ones in the
Yeah.
bottom left, that we don't have many uh, detections for some of those because they were not very bright and faded very quickly.
Right. And then we got this one. Okay, cool. I am with you. All right.
So it was a really exciting data set to get. But what was interesting is as we gathered more and more of this data, we became more and more aware of how little it fit our standard model.
Okay.
And I often say the more data you have, the less it makes sense. And this was absolutely true for this event.
Okay. Well, I'd rather have more data than less.
Yes, me too, except, it can be a little bit tough sometimes to uh, understand what's happening. But
Hmm.
we even though we knew it wasn't going to fit our standard model, the first step is always fitting it to the standard model anyways to get a rough idea of what's going on.
Okay.
And so we have a really sophisticated radio or broadband afterglow modeling code developed by Tanmoy Lasker.
Good.
And we used that to fit all of this data. So in figure 4, I believe that is where we show off these broadband models for this data set.
Figure 4. Let's slide down. Table 4, VLA observations. Host galaxy, and we
It
get
is a very packed paper.
prospector.
Oh, I guess it would be figure 5, my bad. Okay, yeah. Figure
Oh,
4 is stuff about the host galaxy. The
hmm.
host galaxy is completely normal and typical for a uh, short GRB. Nothing surprising there, I would say.
Yeah, yeah. That looks fairly pretty normal. Okay.
A beautiful fit done by Anya Nugent, so I super appreciate her. And I'm
Thank
also now
you.
realizing it wasn't figure 5 either.
All good. Where do you
So
want to
many
go?
figures in this paper.
Oh, man. Where do you want to go? 6?
So yes, figure 6.
Okay. Let's slide down to figure 6. And here we go of the forward shock fitting. Okay.
Yeah, here we go. This is a good overview. This shows all of the beautiful afterglow data that we had gotten. Again, it was
Wow.
a
Okay.
huge effort to detect all of these different detect this afterglow in all of these different bands. So I super appreciate everyone that put in the effort to do this.
Wow. Very cool. Very
Yeah.
cool. Okay. All
So
right.
what we're looking at here is all of the dots. Those are our data points with like error bars. Sometimes the error bars are so small you don't see them, but I promise they're plotted.
And they're like right here. You can see a little bit there and a little bit there. They're there.
Exactly.
They're there. Okay.
Yeah. So we have all of these data points, but we uh, noticed that the early time data, so before about 1 day, was kind of acting a little bit funky.
Okay.
So if you look at the X-rays, which is the topmost data, the 1 keV,
Yes.
you can see that there's this weird little flare that happens. Yep, right around there.
Right around here. Mm-hmm.
And
Hmm.
then there seems to be a weird little plateau that's happening right after that.
Yeah, it kind of goes down, hangs out for a while, and finally drops. Okay. Uh,
Yeah. So that indicated to us immediately that there was something strange going on.
so,
Um,
so let me be clear here. The lines are the model.
yes, the lines are the model.
Okay.
Uh,
It's not a best fit or anything like that.
yes, exactly. It's
Okay.
a physical model that has like physical properties to it.
Okay. I'm with you. Mm-hmm.
Um, and so, yeah, what we did is we took a look at this data. We realized that some of this data didn't make sense compared to our expectations. So we masked that. That's why some of these dots have like holes in them.
Yeah.
We
Okay.
we told our model, ignore that. We know something funky is going on. Let's only look at what doesn't seem super funky.
Okay.
Um, and so, yeah, you can see that the lines, which are our models that correspond to this table 5 that's right next door,
Mm-hmm.
uh, they go through the non-dotted points pretty well, and we're happy about that.
Yeah. Yeah. Okay. Mm-hmm. Particularly later times. Mm-hmm.
Yeah. But you'll see, yeah, for the top, the X-rays are over-predicted, so the line goes above all of the data points.
Yes.
But then if you look at the radio, which is the bottom section,
Mm-hmm.
the lines underpredict our radio.
Yes.
So
Okay.
that is, and also the optical is a bit overpredicted as well, which you can see in the middle section there, the GRI
Yeah.
and I.
Okay. And why do some of the bottom of the radio ones have like these envelopes to them? I guess.
Yeah, so those are scintillation bands. As the radio waves move
Ah,
through electrons, they get a little wobbly.
sure.
And this happens especially at earlier times, which is why the bands are wider at earlier times,
Got it.
because the like size of the source is very small. So it means that it's more likely that the waves will get diverted by random electrons.
Okay. Cool. I'm with you.
Yeah.
Very good. Good.
So, we have this model. It does an okay job, but obviously we're not super satisfied with it. So we wanted to try and figure out a more physical interpretation for what is happening at this earlier time.
Good. Okay.
And so that brings me to figure 7, I believe, the
Figures.
big figure.
A big figure. Let's go to figure 7. This is a big one, so I'm going to zoom out until we get it all, and then I'll zoom in as need be. Okay, let's try that.
Yeah, so just to sort of start, our typical picture of what a GRB jet looks like is, again, we have this central engine. This is after the two neutron stars merge. Um, this central engine is either a neutron star or a black hole,
Mm-hmm.
and it launches this relativistic jet, which you see in gray.
Yes.
And as that jet interacts with the interstellar medium, which is the blue, I guess it's outside of the blue, it will shock that interstellar medium, the outside of the jet, which is the blue part. And
Mm-hmm.
that is what we know as our forward shock.
Okay.
But there's this idea that there could be some additional ejecta launched at maybe a later time or at slower speeds, such that it's sort of hiding behind this initial shell. So we'll see the emission from this initial shell, which is blue here, but then hiding behind it is this pink shell that is starting to catch up to the outer shell as the outer shell is slowing down. It's basically a snowplow. And
Uh-huh.
so eventually it's going to gather up too much stuff on the outside and it will have to slow down because it can't move as fast.
I'm with you. Cool.
So as this pink inner shell catches up to the outer shell, it will not only give the outer shell a bit of energy itself, but it will also sort of get shocked by the outer shell. It's kind of like hitting a brick wall. It's like, oh, something's there. And so it produces this reverse shock that propagates backwards.
Mm-hmm.
And
Mm,
so you can see here this purple emission where these two different things of energizing the forward shock, but then also producing this reverse shock. It gets a little muddied together.
sure. Yeah, you've got interacting system going on. Okay. Um,
Yeah, so you can see here I have on the right, sort of what we would expect both the X-rays and the overall SED to look like.
okay.
And so in the top, the X-rays are falling as expected in this nice little power law.
Mm,
Um, the overall spectrum is just this nice broken power law spectrum that we expect. But
yep.
then as this shell starts to mess with everything, this inner shell starts to mess with everything, the
Yes.
X-rays start to plateau a little.
A little bit. Yes.
And then you can see that the broken power law spectrum, the solid one is the one that's getting energized, and that overall is being moved up.
Yes.
But then this reverse shock, it actually mostly happens in the radio and maybe the optical. So
Mm,
there's this extra little bump in the radio.
yep. Right here. Mm-hmm. I'm with you.
And
Okay.
so eventually, this inner shell will have deposited all its energy into the outer shell. And also, the reverse shock will have like chilled out and calmed down. And so then we just end up with this regular broken power law spectrum again
Yep.
and our regular decay, but it just has a little bit more energy now.
Yeah, you can compare this curve here with this one here. Both
Yeah, so you can even see
logically.
the
Mhm.
dotted blue is our initial one.
Ah,
And so
good.
you
Okay.
can see
Ah,
how the pink is higher now.
got it. I'm with you. There's a refresh. Okay. Oh, good. You got that on there. Very cool. Okay, that's very helpful. Good. Okay.
Yeah, so this is the physical picture of what we think is going on in this system. And it's not like we came up with all of this on our own. This is decades in the making of theory that, and also previous observations have shown that these types of things do happen in GRB afterglows.
Cool. Okay.
Yeah, but we wanted to apply this to our own observations, which brings me to the next figure, which demonstrates sort of how this all comes together.
Okay, let's get into figure 8. This is a comparison
Yeah.
of the FS Afterglow dotted lines. Yes. Okay.
Yeah, so the initial one that I had shown you in that other light curve figure, that is the dotted line. We know that one doesn't work.
Right.
And we have two versions of this refreshed forward shock plus reverse shock model. So those are the solid and the dashed lines.
Okay.
Basically, we like tweaked a few parameters here and there just to see what happens. Overall, we prefer the solid line model because that hits the optical at early times. It does a pretty good job with the X-rays.
Gets it
And
low. Yeah.
yeah, and importantly, the 9.5 gigahertz, so the very bottom radio, um, it the solid line goes through those early points.
Yes. Okay. Very
So
cool.
the dashed line, it does a okay job. It does a really good job at the X-ray side of things. It fits uh, that plateau very well, but it
Raw.
does a pretty bad job at the radio. So that's why we don't prefer it as much, but it could still be an actual,
Mm.
like a legitimate model.
And what is the difference between Model 1 and Model 2?
So we
Physical.
changed the start of when uh this like shock happens basically,
Okay.
and we changed just a few of the parameters inside it.
Okay. Okay. So basically the start time and some of the properties of the forward and reverse shock. Okay.
Yes.
I am with you. Cool. Beautiful figure.
Now, I know that Gemma Anderson actually is writing her own paper on this event. She is the one that is going to publish all of the ATCA data. And I saw a sneak peek of her model, and it's super cool. I'm very interested to see the whole write-up. So
Yeah,
I would
that's
not,
a good shout out.
yeah, I would not take this model as gospel. It's just us trying to figure out maybe what's happening. But I think their model will be very cool to look at once it's out.
Very nice. We'll be looking forward for that one.
Yeah.
Okay.
But so, we did all of this modeling. This is what is typically done in a short GRB Afterglow paper, but this was also going to be the final paper of my PhD. And so I had been sitting on a bunch of radio data that just wasn't super interesting, but we wanted to get it out somewhere.
Okay.
So we decided that this is as good of place as any. And so we broadened this paper not just to this afterglow, but to look more at the radio detected population of short GRBs as a whole.
Ah, yes, yes, yes. Okay, so let's put it in context. Yep.
So if you want to just quickly go back up to figure 3,
I would be.
um,
We'll start getting into some populations. Okay, let me get going there. Figure 3.
yeah, so unfortunately, the way that I did this, I ordered them by redshift and not by time. But if you just briefly look at all of the GRBs on the side,
Yes.
uh, they are named first year, month, day.
Yes.
And so if you look at all of them, you'll notice that there's like 2 from 2005, a
One.
couple from like the 2010s, and then a
Good.
couple from the 2020s.
Okay. Okay. Yes.
And the thing here is for a long time, we were just not very good at detecting short GRBs at radio wavelengths. This is all of them that have ever been detected.
Okay.
And yeah, again, 2 from 2005 and then nothing until what, 2013, I think is the next one.
Yeah.
So
Yes, right here. Yep. Uh-huh.
that
So,
was 8 years without a detection at radio wavelengths. And not for lack of trying. We were trying to observe, but it was not uh, very fruitful.
okay.
And so the fact that in the 2010s and the 2020s, we started to get way more of these detections, it sort of demonstrated to us that it wasn't an intrinsically dim population. It was probably just our radio telescopes and our observing strategies that made it harder for us to detect them.
Okay. Okay.
So moving back to our radio detected population, sort of the second half of this paper,
Hmm.
now that we have this population of about 17 short GRBs with radio detections, we can start to compare them to the overall population.
Yes.
So I think the exciting figure is figure 9, I believe.
Can do
It
9.
sort of pulls it all together.
Well, I like those figures. 7. Let me back off here. 7, 8, and 9. Ooh, good.
Oh, yes, perfect. Yeah.
Okay.
So this is sort of the culmination of most of our knowledge. There's like two other figures that also have some good knowledge in them, but this is a lot of it. And so here, what I was doing for this paper is to take all of the short GRBs with X-ray detections. We needed to do this X-ray detection cut because it helps us localize the events.
Yes.
The gamma ray only detected events are really hard to find anything from. So gamma ray telescopes, the best ones have like arc minute detectors.
Okay.
Some of them are degrees, and for
Great.
those that don't know, that's a huge chunk of the sky. A
Large.
lot of galaxies could fit into those yeah, those localizations.
Yes.
Whereas the X-rays brings it down to 2 to 5 arc seconds.
Oh, much better.
So there have been a few short GRBs that have ambiguous hosts because there's still a couple galaxies in there, but typically 2 to 5 arc seconds, as you had seen in one of my previous figures, like that really helped localize. There was only one galaxy that it could possibly be.
Yep. Figure 1.
So, and we want to have these X-rays because it tells us, where to point our optical and our radio telescopes as well, of course.
Okay.
So
Okay.
here I'm showing you a couple different histograms. And what you should know is that the radio detected, those are the green.
Hmm.
Um, those that were observed in the radio but were not detected, those are striped. And those that were not radio observed at all, those are blank.
Gotcha.
And so this top left is just redshift.
Okay.
Now, we detect short GRBs out to decently high redshifts. It depends who you ask. So we detect them out to about redshift of 3,
Yeah.
but long GRBs we're detecting out to redshift 8 or something. So
Yes.
it depends who you ask, but um, we can detect them to a pretty high redshift.
Hmm.
And uh, but when we look specifically at just when we're detecting them in the radio,
Yes.
we're actually detecting them at much lower redshifts.
Yeah.
So the radio detected population has a median redshift of about 0.5,
Okay.
whereas the overall redshift median for short GRBs is 0.6. So that doesn't seem like a huge difference. But you can sort of even see that like beyond zero point 0.6, we only have 3 radio detections, but we
Okay.
have half of the short GRB population out there.
Yes. Hmm.
So
Okay.
why are we detecting them only at low redshifts? Well, the answer is things are brighter when they're closer.
Yes.
So it's not surprising, but it's good confirmation of like, okay, we're good at detecting things at lower redshift. And the GRB in question for this paper, 231117A, as I had mentioned earlier, it's pretty low redshift compared to the overall population.
Yes. It's right in there. Yes. Okay.
And then since we made this selection cut of it must have X-rays, we also want to sort of look at what the X-ray properties look like.
Okay.
So the middle left is the X-ray flux at zero point 0.1 days. Now
Okay.
we did this because zero point 0.1 days is typically when some of that weird behavior has calmed down. You saw in this one that it had like that weird flare and stuff.
Right. Right. Yeah.
Typically by 0.1 days, it's calmed down.
Okay.
And also it's still detectable because sometimes they'll fade beyond detection after zero point 0.1 days.
Okay.
And here you might be able to pick it out by eye. I have like the stats in the paper itself, but the median of the radio detected is a good portion higher than the overall population.
Yes. Okay. Mm-hmm.
And see, yeah, there's this big chunk of like non-detected around like 10 to the minus 12, whereas most of the detected is above 10 to the minus 12.
Okay. And
Um,
and that's still our GRB right here. That's the dash line. Okay. Uh-huh.
so it's not super special in terms of X-ray properties.
Good.
Um, but if you're wondering, oh, why is the like X-ray flux like sort of correlated with the whether or not we're going to detect them in the radio, it's because you saw that broken power loss spectrum from that big figure.
Yes.
X-ray and the radio are anchored to the same point, which is the peak of that spectrum.
Ah,
So if the
okay.
X-ray is higher, the radio is going to be higher.
With you. Yeah, we're normalizing the peak.
Yeah. So if it's brighter in the X-rays, it's likely to be brighter in the radio, and we're likely going to detect it.
Good. Good. Okay.
Now, on the bottom left, what we're seeing is X-ray luminosity.
Hmm.
So this is basically normalized by distance. And what's really good here is that you can
Okay.
see the radio detected population spans pretty much the whole gamut here. We
Yes.
have it as some of the lowest luminosity and some of the highest luminosity.
Order the magnitude. Yes.
So
Hmm.
that's really good because it's telling us that our radio detected population isn't intrinsically different from the overall population.
Yes.
We have some observational biases due to how close it is and how bright it is.
Yes.
Overall, we're not detecting a specific type of short GRB afterglow.
Yeah. That's what that would suggest. Yes. Which is good.
Yes, it's very good. Um, and
Okay.
then on the right, we have two other properties, the circumburst density and the offset from the host galaxy. Now, the circumburst density is, again, that's the, yeah, top right.
Hmm.
Um, that is how much stuff is around this neutron star merger.
Yes.
And, because this jet is interacting with that stuff, and that interaction is what causes this afterglow,
Hmm.
you can imagine that the more stuff around, the brighter the afterglow will be.
Okay. Okay.
And this is especially true at radio wavelengths, which are super sensitive to how much stuff is around this merger.
Right.
And you can see that here, where a lot of our radio detected population is at pretty high densities compared to the overall population. This is the uh, property that we saw the starkest contrast in the medians. I
Yeah.
believe the radio detected population median was an order of like a factor of 10 higher
Yes.
than the overall population.
Okay.
So this is just showing us that like our understanding of the forward shock model, even when things get a little funky, the forward shock model is still pretty consistent with what we're seeing.
Hmm.
And yeah, we are detecting things when they have more stuff around them.
Makes sense.
And then you might start to think, where are you finding all this
Yeah.
stuff?
Where?
Yeah, in this galaxy. And you might think the closer you are to the middle of the galaxy, the more stuff you would have around.
Mm, okay.
You might think it.
Let's say I thought that. Let's say I thought that.
Let's say you thought that. So that's why we sort of took a look at the offset of these uh, of the population.
Uh-huh.
So again, we're seeing that these radio detected events are typically at a lower offset, so they're closer into their host galaxies
Okay. Mm-hmm.
than the overall population. They can be kind of far away,
Mm-hmm.
but oftentimes they are closer.
So is it true then that the closer we are, that would correlate with higher N0?
What a great question. If we move on to the next
Oh,
plot.
my anticipation here. My anticipation here. Okay, so figure 9, let's slide down to figure 10, and we'll get what I wanted, which is N0 over delta R. Okay.
Yeah.
There we go.
Yeah. So that was what we were curious about too, is like, oh, if we're at higher density
Hmm.
and lower offsets, is there any type of correlation? The answer is maybe. I wouldn't say correlation, that is a statistical word, and I did not do any stats. I just plotted things and looked for trends.
Yes.
Um, but what you can see is that at low, regardless of radio detection even, at low offset, so
Yes.
like less than 10 to the 0,
Hmm.
it's like not a lot at low density, so less than 10 to the -2. There's
This
kind of,
area is empty. This one's populated. Yep.
yeah,
Hmm.
so you can kind of think that there might be a trend in that. Again, I don't want to say anything too strong because I did no stats for this, but it does seem that there is some trend of
Yeah.
high density and low offset.
Mm.
But of course, you can see you also get high density at high offset as well,
This one right here. Hmm.
but it's hard to get low density at low offset at least.
Yes. Okay. That part is clear.
Yeah.
And then it sort of scatters a bit.
Yeah.
Okay.
So I and there's, a lot of nuance to this. The like ways that these like densities were derived were not necessarily uniform.
Okay.
So I
Okay.
think it could be interesting to look more into in the future. The offsets were pretty uniformly derived at least, but the densities, they have some nuances to
Yeah,
them.
that's
But
got a few more steps in it. So yeah. Okay.
I do think it's interesting to see at least this dearth of stuff at the low density, low offset.
Yes. The void
Yeah, the void.
here. Cool.
Yeah.
Okay.
And then another property that we thought was really interesting to look at was the jet opening angle.
Oh yeah.
So, yeah, how wide is this jet and how is that affected, or how does that affect the radio afterglow? Um, so you might first ask, why do you care about the jet opening angle? And I would say it helps us know how many of these events happen. So you can imagine if we're only detecting
Ah,
stuff where the jet is pointing at us,
yes. Okay.
then there's probably some events where the jet is not pointing at us. And we know from GW 170817, which again is this binary neutron star merger that has a short GRB detection,
Uh-huh.
from modeling that, we know that it was actually a little bit offset. So the jet was sort of pointing at us, and then as it spread is when we actually got to detect it.
I see. Okay. Hmm. Got it.
So knowing how tightly collimated these GRB jets are helps us know how many of them are pointing not at us
Yes.
and lets us know how many of these events we are not detecting.
But we might expect. Yes. Okay.
Yeah.
Okay.
But then determining that jet opening angle is difficult because we need a couple key factors. We need some of these afterglow properties. So we need how much energy is in the jet,
Okay. Yes.
need the circumburst density,
Yes. That's the other part.
need the redshift, of course.
Hmm.
Um, and
Distance.
then we need to know when the afterglow itself starts to change its behavior. So the afterglow will start to steepen at a point
Mm-hmm.
that makes it that is called a jet break, and that tells us that we have started to see the edges of the jet.
Okay. Okay.
This is due to like beaming effects and stuff I don't really want to get into, but it's what's important is that that is an observable property in these like data points that we collect.
Okay. Nice.
So moving on to figure 11.
Yeah, so there we go. Opening
We're
angle.
back to histograms. I loved a histogram for this paper.
I get them too. Very good. Okay, let's blow that up a little bit.
And so this histogram represents all of our current knowledge on the jet opening angles of short GRBs. There's only 30 or so events in this sample.
Yes.
Um, so I think one of the first most interesting things is that there's only 30 or so events, but a lot of radio detections. So this had the highest percentage of detections for the overall population.
Cool.
It was like 40%.
Cool.
Uh, So that automatically tells me that radio detections are really important for determining the jet opening angle.
Yes.
And then you might also see that we have these arrows pointing towards higher jet opening angles.
Yes, lower limit.
So if we are looking at the afterglow and we don't see that steepening that I talked about,
Yes.
that means that we can't constrain what the jet opening angle is, but we can get a lower limit where we can say, well, if we didn't see it, then we know it must be at least
Use
this wide.
this. Okay.
Otherwise, we would have seen it.
Okay.
And so not only are the radio detected population overall very important for this, but you can see only two of the detections have lower limits. All the other ones are constrained.
Yes.
So
Mm-hmm.
the radio afterglow in combination with these other wavelengths is really important for constraining this actual opening angle.
Cool. Okay.
And
Mm-hmm.
then you'll also notice that past 10 degrees,
Yes.
all of the constraints are radio detected.
Yes. Fairly
Yeah.
wide one out there, but
Yeah.
otherwise fairly narrow, right? 10, 15 degrees, somewhere in there. 5 to 15. Mm-hmm.
So when we have these wider jets, what happens is the optical and X-ray, they're already fading. And then sometimes they'll fade below detection before we see the steepening in their light curves.
Okay. Mm-hmm.
But the radio is one of the only parts of the afterglow spectrum that actually has a rise at first, in some cases at least.
Mm-hmm.
And so, and even once it does start to fade, it typically fades at a slower pace than the optical and X-ray.
Okay.
And so that's why all of the wide jets above 10 degrees have been radio detected. It's due to the fact that our radio observations are more sensitive to these late time steepenings that we can't detect as well in the optical and the X-ray.
Okay, I'm with you. Mm-hmm. Mm-hmm.
Yeah. So it was really cool to sort of like see all of this laid out in
Yeah.
this paper where we like took a look at all of these properties and found that not only are we pretty good at detecting the radio actually, but we now know like why we're good at detecting the radio and
Yeah.
in what circumstances we're not as good at detecting the radio.
Okay.
So I would say the overall conclusion is like this one event was really interesting and has a really unique afterglow that I'm glad that we followed up. But also the radio detected population as a whole is just super interesting and holds a lot of information.
Mm-hmm. Mm-hmm.
And I would say, of course, more radio observations always, even if they start to not follow what you would expect in terms of the like forward shock.
Yes. Yes. Very cool. Very cool. Beautiful work. Beautiful work.
Thank you.
Genevieve, I want to thank you so much for walking us through your very awesome article on GRBs and their population. Very nice.
Yeah, thank you so much.
Sure. Let's see. And you mentioned it there a little bit at the end, so I'll push on it a little bit. And where do you think we go from here, given the published article, to either better characterize this particular GRB or the population itself? Just sort of, next steps. Where do you think we go over the next couple of years?
Yeah, that's a great question. What I will say first is I didn't really get into it, but I mentioned that we had these two 2005 events, and then we started detecting stuff in the 2010s.
Uh-huh.
In between that, the Very Large Array, which has been, a workhorse in following up these events, it got a major upgrade where it became 10 times more sensitive.
Nice.
And I think that the fact that we then started being better at detecting these events really demonstrates that, again, it wasn't that they were just intrinsically dim or undetectable, but just our instruments were not as good.
Sensitive. Yes. Okay.
Um, and in a previous paper that I had published, I also found that we had a secret population of late rising radio afterglows. So I detected something that like was undetected up until 10 days, and then it like had a really weird radio afterglow.
Okay.
Um,
Okay.
More reverse shock and refresh shock stuff.
Yeah. Yeah.
But so I think that really demonstrated to me that we were observationally biasing towards like these quicker fading events, but these slow rising events were not being observed as well. So my main thing is just like more sensitive telescopes and observing for later times that will really help us understand this radio, uh, this short GRB population in the radio.
Hmm.
Um, the next generation very large array is supposed to be like even more sensitive. So I'm really excited for that in terms of short GRB follow-up because it should probably detect like all of them, you know, like it's going to be
Complete.
super exciting.
With
Um,
distance.
yeah, exactly.
Very cool.
But then also I had talked a little bit about how the X-ray afterglow is also like connected to whether or not we'll detect it in the radio.
Yes. Yes. Could you do that cut? Hmm.
Yeah, and so I think what we should do is in the future when we have a like dimmer X-ray afterglow, maybe that means we should go deeper in the radio
Okay.
because we know that the radio is likely to be less bright.
Okay. Cool.
Yeah. So
Well, it's going
it's
to be very exciting to see this develop over the next couple of years with NGVLA, and hopefully our X-ray satellites stay operational. It'll be great. Very.
yeah, and have more put up just in case.
Yeah. Yeah. Okay. Very cool. All righty, Genevieve. Thank you so much once again for walking us through your very lovely article.
Thank you. It was super fun and I'm glad we got to chat.
It was fun. And that'll do, everyone. And I hope this made your short GRB day just a little bit better. And we will see you on the next one. Bye bye.